Welcome! Today, we'll be solving an intriguing coding problem, smallest missing genetic value in each subtree, also known as problem number 2003. This problem challenges us to work with tree structures and missing values in a genetic sequence. By the end of this session, you'll gain a deeper understanding of efficient tree traversal techniques and how to identify missing values systematically. Let's dive in. In this problem, we are working with a tree represented by an array called parents. The tree has n nodes, and it is rooted at node 0. Each element in the parents array tells us the parent of that node. If a value in the parents array is -1, it means that node is the root. Alongside this, we are given another array called nums that represents the genetic values of the nodes. Each value in nums is unique and lies within the range 1, n. Now, the goal is to determine, for every node in the tree, the smallest missing genetic value in its subtree. A genetic value is considered missing if it falls in the range 1 en, but does not appear in the subtree. Finally, we need to return an array result, where each element corresponds to the smallest missing genetic value for the subtree of the respective node. To understand this problem better, let's look at an example. Consider the input parents equals -1, 0, 0, 2, and nums equals 1, 2, 3, 4. In this case, the output is 5, 1, 1, 1. Here's the breakdown. Node 0 has the subtree 0, 1, 2, 3, and the genetic values in this subtree are 1, 2, 3, 4. Since all values between 1 and n are present, the smallest missing value is 5. For node 1, its subtree contains only itself, and its genetic value is 2. The smallest missing value becomes 1 because 1 is not present. Similarly, the subtrees for node 2 and node 3 contain genetic values 3, 4, and 4, respectively. In both cases, the smallest missing genetic value is also 1. Building on this, here's another example. For the input parents equals -1, 0, 1, 2, and nums equals 1, 2, 3, 4, the output is 1, 1, 1, 1. Let's analyze why. Node 0 has the subtree 0, 1, 2, 3, and the genetic values in this subtree are 1, 2, 3, 4. Since all values from 1 to n are present, no genetic value is missing, so the smallest missing value is 1. For nodes 1, 2, and 3, their subtrees contain genetic values 2, 3, and 4, respectively. For all of these, the smallest missing genetic value is also 1 because it is not present in any of these smaller subtrees. Now let's consider a slightly different example. If we have parents equals -1, 0, 1, and nums equals 2, 3, 4, the output becomes 1, 1, 1. Here's why. Node 0 has the subtree 0, 1, 2, and the genetic values in this subtree are 2, 3, 4. The smallest missing value is 1 because 1 is not present in the subtree. For node 1, its subtree includes itself and node 2, with genetic values 3, 4. Again, the smallest missing genetic value is 1. For node 2, its subtree is only itself, with a genetic value of 4. The smallest missing value is still 1. This example highlights cases where genetic values do not start at 1. The problem also has some constraints and edge cases to consider. For example, the size of the tree, n, can go up to 100,000, so we need to ensure our solution is efficient. Additionally, the parents array always starts with -1 for the root node, and all other values are valid indices within the range 0 and 1. The nums array contains distinct integers in the range 1 en, which simplifies the problem since there are no duplicate genetic values. Now, let's look at some edge cases. In a single node tree, like parents equals -1 and nums equals 1, the output is 2, since the only node already has the value 1. In a tree where all nodes are in a straight line, such as parents equals -1, 0, 1, 2, and nums equals 4, 3, 2, 1, the output is 5, 1, 1, 1, because node 0's subtree contains all values from 1 to 4, and all other nodes have missing values starting at 1. Finally, consider a larger tree with missing values, like parents equals -1, 0, 0, 1, 1, and nums equals 1, 2, 5, 3, 4. Here, the output is 6, 6, 1, 1, 1. Node 0's subtree includes all the nodes, with genetic values 1, 2, 3, 4, 5. The smallest missing value is 6 because it is the first value greater than 5. For node 1, its subtree includes nodes 1, 3, and 4, with genetic values 2, 3, 4. The smallest missing value is also 6 since 5 is not in this subtree. For nodes 2, 3, and 4, the missing genetic value is 1 because their subtrees only contain their own genetic values. These examples illustrate how the problem scales and handles edge cases effectively. To solve this problem, we first considered a brute force approach. The idea here is straightforward. For each node, we traverse its entire subtree, collect all the genetic values, and then determine the smallest missing value by starting from 1 and checking incrementally. While this method is intuitive, it involves traversing the subtree of every single node, which means we perform an O(n) traversal for each of the n nodes. This leads to a time complexity of O(n squared, making it highly inefficient for large inputs. Another approach we explored is using a union-find data structure to track connected components dynamically. Union-find is generally efficient for union and find operations, with an amortized complexity of O(alpha n). However, the challenge lies in efficiently detecting the smallest missing genetic value, which union-find does not handle naturally. This adds unnecessary complexity without directly addressing the problem, making it less suitable for this case. The most efficient solution leverages a combination of bit masking and depth-first search, or DFS, with a globally maintained visited array. The key insight is that the smallest missing genetic value in a subtree is determined by the genetic values present in that subtree. By marking values as visited globally, we avoid the need for repeated subtree traversals. To implement this, we first perform a DFS to build the tree structure. Then, we conduct a reverse DFS starting from the node with genetic value 1, marking all encountered genetic values as visited. For each node, we determine the smallest missing genetic value by incrementing a counter until we find an unvisited value. During the backtracking phase, we propagate the visited states up to the parent nodes, ensuring that each node is processed efficiently. This approach has an overall time complexity of O(n), because each node and edge is traversed only once, and genetic value checks are streamlined using a Boolean array. While the implementation of reverse traversal and state merging requires attention to detail, this method is computationally optimal and scalable. The chosen strategy is the DFS with a global visited array, as it combines efficiency and clarity. The key breakthrough lies in recognizing that the smallest missing genetic value can be determined during the backtracking phase. By propagating visited states during the reverse traversal, we avoid redundant subtree traversals and ensure that each node is processed optimally. Comparing alternatives, the brute force approach, while simple, is computationally prohibitive for large inputs due to its O(n squared) complexity. Union find, though dynamic, does not provide a direct mechanism for detecting missing values efficiently. The DFS with a visited array balances these trade-offs, offering an elegant solution with a time complexity of O(n) and a space complexity of O(n). This strategy ensures correctness and handles the problem constraints effectively, making it the optimal choice for solving this problem. To understand this problem, imagine we have a tree with n nodes, where each node is associated with a genetic value. The task is to find the smallest positive integer that doesn't appear in the genetic values of a node's subtree. A subtree includes the node itself and all its descendants. For example, if a subtree contains genetic values 1, 2, 3, the smallest missing value would be 4, as it's the first positive integer not in the set. To solve this, a straightforward brute force method begins by representing the tree as an adjacency list. This is a common and efficient way to model tree structures, where each node points to a list of its child nodes. Using this representation, we can traverse the subtree of any given node, gather all genetic values, and determine the smallest missing value. Let's break these steps down further. Once the tree is represented as an adjacency list, the next step is to traverse the subtree of each node. For this, we can use either depth-first search, DFS, or breadth-first search, BFS. The goal is to visit all nodes in the subtree, ensuring each node is only visited once by using a set to track visited nodes. As we traverse, we collect the genetic values of the visited nodes into another set. After this, we determine the smallest missing genetic value by starting with 1 and checking if it's in the collected values. If it is, we increment the value by 1 and check again, repeating this process until we find a value that's not in the set. This value is the result for that particular node. Finally, we store this result in an array and repeat the process for all nodes in the tree. Once every node has been processed, we return the results array. Here's how these steps look in code. In the code implementation, we first build the tree using the adjacency list approach. Then, we define a helper function for DFS traversal to collect genetic values from a node subtree. This function uses a stack to simulate the recursive nature of DFS. We iterate through the nodes in the stack, keeping track of visited nodes to avoid revisits, and add their genetic values to a set. For each node, we calculate the smallest missing value by checking if it's in the set of collected genetic values. If it is, we increment the value until we find one that's missing. This process is repeated for every node, and we store the results in an array. The function then returns this array as the final output, representing the smallest missing genetic values for the subtree of each node. The brute force approach, while straightforward, has a time complexity of n squared, in the worst case. This is because for each node, we traverse its entire subtree, which can involve visiting all n nodes. The process of determining the smallest missing genetic value is efficient due to the set's constant time average lookup, but the repeated traversal of overlapping subtrees makes the approach inefficient for large trees. To implement this approach, we rely on key data structures such as an adjacency list for tree representation, a set for fast genetic value lookups, and a stack or queue for DFS or BFS traversal. It's also important to consider edge cases, like when the tree has only one node, where the result will always be 1, or when all nodes have the same genetic value, causing the smallest missing value to increment linearly. Edge cases also include scenarios like sparse trees, where nodes have few children, and dense trees, where nodes have many children, as the traversal cost depends on the tree's depth and branching factor. To optimize the brute force approach, we can pre-process the tree to avoid redundant computations. For example, instead of recalculating subtree values for each node, we could use a single traversal to compute results for all nodes simultaneously. Advanced techniques like union find or lowest common ancestor (LCA) algorithms can help achieve this. These methods reduce overlapping subtree calculations, significantly improving efficiency, especially for larger trees with many nodes. To solve this problem, we start by importing the necessary libraries. Here, we use defaultdict from the collections module to create an adjacency list for the tree structure. Then, we define the smallest missing value subtree function within the solution class, which takes two main inputs, the parents array representing the tree structure and the nums array containing genetic values for each node. The first step in the function checks if the genetic value 1 is absent in the nums array. If 1 is not present, then all nodes in the tree will have 1 as their smallest missing genetic value, so we return an array filled with 1. Next, we build the adjacency list using a loop over the parents array. Each parent-child relationship is added to the tree dictionary, skipping the root node which has a parent of -1. After constructing the tree, we initialize the result array with 1 for all nodes, as 1 is the default smallest missing value before any computation. We then locate the index of the node where the genetic value 1 exists in the nums array and store it in 1_index. Additionally, we create a visited set to keep track of genetic values encountered during traversal. Finally, we define a helper function DFS for depth first search, which will recursively explore the subtree of a given node and add genetic values to the visited set. The depth first search function, DFS, starts by marking the genetic value of the current node as visited. Then, for each child of the current node, the function recursively calls itself to explore deeper levels of the tree. After defining DFS, we focus on traversing the tree from the node containing the genetic value 1 upwards to the root. We initialize current with the index of this node, stored in 1_index, and set missing to 1, as we aim to find the smallest missing genetic value starting from 1. In the while loop, which continues until we reach the root, we first call DFS on the current node to mark all genetic values in its subtree. Next, we incrementally check for the smallest missing genetic value by testing if missing is in the visited set. If it is, we increase missing until we find a value not in the set. This value is then stored in the result array for the current node. After updating the result, we move current to its parent using the parents array. Once the loop completes, the result array contains the smallest missing genetic value for each node subtree, and we return it as the final output of the function. Here, we're starting by importing the necessary Java utilities and defining our solution class. The method smallest missing value subtree begins by taking two inputs, the parents array, which represents the tree structure, and the nums array, which contains the genetic values for each node. The first step is to check if the value 1 exists in the nums array, since this is a critical edge case. If 1 is not present, we can immediately return an array filled with 1 for all nodes, as the smallest missing value in every subtree would always be 1. To achieve this, we use a Boolean flag contains 1 and iterate through the nums array to set it accordingly. If 1 isn't found, we create a result array, fill it with 1, and return it. Now, assuming 1 is present, the next step is to construct the tree as an adjacency list. We initialize the tree as an array of lists, and for each node, we add its child to the corresponding parent node's list. This will allow us to traverse the tree efficiently in subsequent steps. Once the tree is built, we initialize the result array, filling it with 1 as the default value for all nodes. Next, we determine the index of the node where the genetic value 1 exists. We iterate through the nums array, and as soon as we find the value 1, we store its index in the variable 1 index. This node is critical because the computation for missing genetic values will begin from here. To handle genetic values within a subtree, we use a set called visited. This set will help us track all genetic values encountered during a depth-first search. We define the DFS method, which takes a node as input. Inside this method, we add the genetic value of the current node to the visited set. Then, we recursively call DFS for each child of the current node, effectively collecting all genetic values in the node subtree. This recursive traversal ensures that we don't miss any genetic values within a given subtree. Now, we begin processing from the node that contains the genetic value 1 and propagate upwards through the tree to compute the smallest missing genetic values for each ancestor. We initialize current as the 1 index and set missing to 1. As long as current is not -1, we perform a depth-first search on the subtree rooted at the current node. This marks all genetic values in the subtree as visited. Then, we incrementally check for the smallest missing genetic value by verifying if visited contains the current value of missing. If it does, we continue incrementing missing until we find a value that isn't in the set. This value is then stored in the result array for the current node. Finally, we move to the parent of the current node by updating current to parents, current. This process continues until we've processed all relevant nodes. Once the traversal is complete, we return the result array, which contains the smallest missing genetic value for each node subtree. To begin solving this problem, we start with an example tree where the parents array is -1, 0, 0, 1, 1, 2, and the genetic values assigned to each node are 5, 4, 6, 1, 2, 3. First, we determine the number of nodes in the tree, which is 6. Since the genetic value 1 exists in the nums array, we can proceed. The next step is to build the tree using the parents array. This creates an adjacency list that represents the tree structure, where node 0 has children 1 and 2, node 1 has children 3 and 4, and node 2 has child 5. We also initialize the result array to 1, 1, 1, 1, 1, 1, with the assumption that every node starts with 1 as the smallest missing genetic value. Finally, we identify the index of the node containing genetic value 1, which is at index 3, and prepare to propagate from this node. Starting from node 3, which contains the genetic value 1, we initialize an empty set called visited to keep track of genetic values encountered during the traversal. Using depth-first search, we visit node 3 and add its genetic value to the visited set. Since node 3 has no children, we move to the next step of determining the smallest missing genetic value. We start with missing equal to 1 and increment it until we find a value not present in visited. Here, the smallest missing value is 2, so we update result 3 to 2. Now, we move to node 3's parent, which is node 1, and repeat the process. At node 1, we add its genetic value, 4, to the visited set. We also visit its children, nodes 3 and 4, adding their genetic values 1 and 2 to the set. The smallest missing value now is 3, so we update result 1 to 3. Next, we move to node 1's parent, which is node 0. At node 0, we add its genetic value, 5, to the visited set and include the genetic values of its children, nodes 1 and 2, to complete the set. At this stage, the visited set contains all genetic values from 1 to 6. To find the smallest missing value for node 0, we start with missing equal to 7, as it is the first value not in the visited set. We update result, 0, to 7. Since node 0 is the root of the tree and has no parent, we stop the propagation here. The final result array for this example is 7, 3, 1, 2, 1, 1. Moving on to a second example, we consider a tree described by parents array, 1, 0, 0, 1, 1, 2, and genetic values, 5, 4, 6, 7, 8, 9. This time, the genetic value 1 is absent from the nums array. In such cases, the result array is simply 1, 1, 1, 1, 1, 1, as there is no propagation process required. The function immediately returns this result. Now let's look at a simpler case, a single node tree. The parents array is -1, indicating that there is only one node, and the genetic value assigned to this node is 1. First, we determine that the number of nodes is 1. Since the genetic value 1 exists in the nums array, we proceed to build the tree. In this case, the tree is empty because the single node has no children. We initialize the result array to 1 and find the index of the node containing genetic value 1, which is at index 0. We then set the current node to 0 and initialize an empty visited set. Using depth-first search, we visit node 0 and add its genetic value, 1, to the visited set. Since node 0 has no children, we move to finding the smallest missing genetic value. Starting with missing equal to 1, we increment it until we find a value not present in the visited set. Here, the smallest missing value is 2, so we update result, 0, to 2. Since node 0 is the root and has no parent, the propagation stops here. The final result array for this example is 2. To analyze the time complexity of our solution, we start with the process of constructing the tree structure. This is done by iterating over the parents array and building an adjacency list representation of the tree. Since each element in the parents array is visited exactly once, this step requires n time, where n is the number of nodes in the tree. Next, we perform a depth-first search, or DFS, to traverse the subtrees. The DFS function processes nodes in a subtree, and in the worst case, a single DFS call might visit all nodes in the tree, leading to n complexity. However, because each node is part of exactly one subtree and is visited only once throughout the entire traversal, the total time spent across all DFS calls is also n. This ensures efficiency as the traversal doesn't repeat work unnecessarily. Now let's examine the step where we find the smallest missing genetic value. The while missing in visited loop checks for the smallest genetic value not present in the visited set, incrementing the missing value until a gap is found. Since the visited set contains only the genetic values found in the tree and there are at most n unique values, the loop runs at most n times in the worst case. This makes the complexity of this step n. Combining all the steps, the tree construction takes n, the subtree traversals via DFS take n, and finding the smallest missing genetic value also takes n. Therefore, the overall time complexity of the solution is n, which is highly efficient given the problem constraints. Next, let's analyze the space complexity. First, the adjacency list tree requires n space since there are n nodes in the tree. The visited set, which keeps track of the genetic values encountered during the DFS traversal, also requires n space in the worst case, as it can store up to n unique values. The recursive call stack depth of the DFS function depends on the tree structure. For a balanced tree, this depth is log n, but in the worst case, such as with a skewed tree, the depth can reach n. Additionally, the result list, which stores the output for all nodes, requires n space. When we sum these contributions, the total space complexity is n, dominated by the space required for the adjacency list, the visited set, and the result list. Finally, let's compare our optimized approach to a naive solution. In a naive approach, we would iterate through all nodes for each subtree, collect the genetic values, and then determine the smallest missing value. This involves processing each subtree independently, leading to a time complexity of n squared, in the worst case, as every node and its descendants would be reprocessed multiple times. In contrast, our optimized approach uses DFS to propagate genetic values upward from the node containing 1, ensuring that each node and its subtree are processed just once. This reduces the time complexity to O(n). Considering different cases, in the best-case scenario where the tree is balanced and genetic values are small, the recursive depth is O log n, improving the space complexity of the call stack while the time complexity remains O(n). In the worst case, with a highly skewed tree and large genetic values, both time and space complexities remain O(n). Finally, from a big O perspective, we can prove the solution is linear because each node is processed exactly once, and each genetic value is checked only once. Combined with the linear contributions from tree construction and result initialization, the overall complexity of the solution is confirmed to be O(n). When tackling this problem, there are several common mistakes to watch out for. One frequent issue is not accounting for duplicate genetic values. If the tree contains repeated values and these are not handled correctly, it can result in errors, such as mistakenly considering a value as missing when it's actually a duplicate. The best way to address this is by using a set to track unique genetic values, as sets automatically ignore duplicates. Another pitfall is inefficient traversal of subtrees. A naive, brute force approach that retraverses the entire subtree for every node can quickly become computationally expensive, especially for larger trees. To avoid this, you can use optimized data structures like union find or segment trees, which allow you to pre-process and query data more efficiently. Lastly, some solutions fail to handle missing values correctly. For example, it's incorrect to assume that the smallest missing genetic value always starts at 1 for every subtree, as earlier subtrees may already contain values like 1, 2, and 3. To prevent this, maintain a global reference that tracks the smallest missing integer across all subtrees, ensuring the solution is accurate and consistent. Another common variation involves misinterpreting the tree structure provided in the input. Sometimes, the tree may be represented as an adjacency list or a parent-child array, and failing to parse this correctly can lead to an improperly constructed tree, which invalidates the entire solution. To avoid this, always carefully validate the input format and ensure the tree is built accurately before you proceed with solving the problem. Additionally, many solutions falter due to skipped edge cases. For instance, you might encounter a tree with only one node, a tree where no genetic values are missing, or a tree where all genetic values are consecutive integers. Neglecting these scenarios can lead to brittle solutions that fail under certain conditions. To make your solution robust, it's essential to test thoroughly using diverse edge case scenarios, ensuring the implementation can handle any input gracefully. From an interview perspective, this problem is often designed to evaluate your ability to optimize a brute force solution into something more efficient. It's not just about arriving at the correct answer but also about clearly explaining your thought process. For instance, you might begin with a simple approach and then identify bottlenecks, such as redundant subtree traversals, and propose optimizations like pre-processing or using auxiliary data structures. Recognizing patterns in the tree structure is also key. Techniques like depth-first search or breadth-first search can help you navigate subtrees more systematically. Furthermore, interviewers may expect you to discuss space-time trade-offs. For example, pre-processing data can drastically reduce the time complexity of queries, but it comes at the cost of additional memory. Demonstrating an understanding of these trade-offs and explaining their relevance to your solution can leave a strong impression. Finally, emphasize the importance of pre-processing, such as pre-computing genetic values for subtrees, as this can streamline your approach and make your solution more elegant. If you're looking to deepen your understanding, there are several related problems that explore similar concepts. For instance, LeetCode 238, product of array except self, involves pre-processing to exclude specific contributions, much like excluding certain genetic values in a subtree. LeetCode 310, minimum height trees, focuses on tree structures and efficient traversal methods, which are highly relevant here. Similarly, LeetCode 323, number of connected components in an undirected graph, uses concepts like union find to identify connected components, a technique that can also be applied to this problem. Finally, LeetCode 128, longest consecutive sequence, emphasizes finding missing or consecutive integers efficiently, which directly parallels the goal of tracking genetic values. As for alternative approaches, optimized depth-first search with a hash set can avoid redundant traversals, though it requires extra space to store visited nodes. The union find algorithm is another powerful tool for managing connected components, though it adds pre-processing overhead. You might also explore segment trees or binary index trees for range queries, which are efficient but more complex to implement. Lastly, breadth-first search is a straightforward method for level-order traversal, but it can consume more memory when dealing with wide trees. Choosing the right approach often depends on the specific constraints and trade-offs you need to balance in your solution. Great job! To recap, we tackled the problem of finding the smallest missing genetic value in each subtree, applying efficient algorithms to solve it. Remember to practice tree-related problems often, as they come up frequently in technical interviews. Thank you for watching, and don't forget to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!